Multivariable calculus, linear first-order differential equations. And there is, in fact, a linear first-order differential equation written in red, and the slope field that goes with it is in green, and several solutions are drawn as blue curves. So let's look more closely now at first-order linear differential equations. The definition is that a linear first-order differential equation is of the form dy dx plus p of xy equals q of x. Now, some special cases. For example, when q of x is 0 and p of x is a constant, then the linear first-order differential equation devolves into dy dx plus cy equals 0. We can bring the cy to the other side, and let's call negative c our k, and that should look familiar. Yes, indeed, you should probably know the solution immediately. It's y equals a constant times e to the kx. All right, now, what if q of x is 0 and p of x is not a constant? Then the linear first-order differential equation devolves into dy dx plus p of xy equals 0. So we're keeping q of x 0 here. These are the easiest of the cases. And so if we move p of xy to the other side, we can then separate the variables and continue by using integration. I'm not going to finish that up, but you know how to do that. Okay, so now what if p of x is 0? Well, then our equation devolves into dy dx equals q of x. We can separate the variables, and that can be easily solved because you're just integrating a quantity in x on the right. So let's look at the more general form where neither p of x nor q of x are 0. What do we do? Well, step 1, believe it or not, this is a little weird, is we let s of x be such that s prime of x is p of x. And then we multiply through by e to the s of x, which is called the integrating factor. So we end up with e to the s of x times dy dx plus e to the s of x times p of xy equals e to the s of x times q of x. Huh? How is that better? Well, check this out. First, note that the derivative of y times e to the s of x is equal to e to the s of x times dy dx plus e to the s of x times s prime of x times y. That's using the product rule and the chain rule, right? Well, surprise, surprise. Looky there. We said that p of x was s prime of x, and so what we have there is the entire left side of the equation. Okay, so step 2 is we set the derivative of y e to the s of x equal to the right side, e to the s of x q of x, and now we integrate both sides with respect to x. And so we get the antiderivative on the left, and we get the integral on the right. Well, now on the right, everything's in terms of x, right? Now, you might have a complicated integral, but the ones in the textbook are going to be doable. And so step 3, you just solve for y by multiplying both sides by e to the negative s of x. And of course, you've got to do the integration. Okay, so let's do an example. Find a general solution for the linear first-order differential equation dy dx plus ay equals b. So p of x is the constant a, and q of x is the constant b. And so s of x is the antiderivative of p, and so s of x is ax. Now here's our formula. You don't have to go through all the steps. You can just use the final result. And so there's our result in terms of an integral. And then that's easily integrated. Don't forget your plus c. And then when we multiply through by e to the negative ax, the first e to the ax goes to e to the 0, which is 1. And there's our final answer. Now, see, that was easy, wasn't it? Okay, so let's look at another example. Find the specific solution for the linear first-order differential equation given that y of 2 is 20, and here's your differential equation. Is it of the right form? Well, we got a problem there with the x squared. It's supposed to start out with just dy dx. So how can we fix that? Well, we just divide by x squared. All right, so now p of x is negative 2 over x, and q of x is 3x to the fourth. And so s of x is the antiderivative of negative 2 over x, which is negative 2 log x. Now there's our formula, and we plug in, and note that e to the negative 2 log x simplifies to x to the negative 2. So when we combine that with the 3x to the fourth, we get 3x squared. And when we integrate that, we get x cubed plus c, and then I distribute it. Now, we put in our 20 for y and our 2 for x and solve for c. And we get c equal negative 3. And so there's our final answer. Y equals x to the fifth minus 3x squared. Okay, let's look at another example. Find a general solution for the linear first order differential equation du dt plus 3u equals sine t. Now don't panic, u is playing the part of y and t is playing the part of x. So p of t is just 3 and q of t is just sine t. So if p of t is 3, then s of t is the antiderivative of that, which is just 3t. Here's our formula in terms of x. And so we get u equals e to the negative 3t times the integral of e to the 3t times sine t dt. Now, that's not so easy to integrate. Do you remember how to integrate something like this? Integration by parts. So let's take a look at that. Here's what we had, and let me rewrite it down here. And we're going to let u equal e to the 3t and dv equals sine t. Or you can do it vice versa, but once you've chosen which way to go, you got to stick with that. We're going to have to integrate twice here. Okay, so du is 3e to the 3t dt, and v is negative cosine t. So let's write in our formula for integration by parts, and we get u times v minus v du, and so the minus negative cosine becomes a positive. Now we have to do integration by parts again, and so I'm going to use different letters. I'm going to let z equal e to the 3t. Notice I'm doing the same thing again. And dw is going to equal cosine t dt. So dz is 3e to the 3t dt, and w is positive sine t. So filling in again, we have what we originally had, negative e to the 3t cosine t plus 3 times the new formula for our second integral there. So we get z times w minus w dz. Okay, now you might notice that we've got the same thing on the right as we have on the left as far as the integral is concerned. So we add 9 of those integrals to both sides, which leaves me with 10 of them on the left, and then just negative e to the 3t cosine t plus 3 times e to the 3t sine t on the right, and then at some point when you integrate you have to have a plus a constant, so I just added plus k. So now we can divide by 10, and we get u equaling the original e to the negative 3t times what we got for the integral. Okay? And then if we multiply through by e to the negative 3t, we get a nicer answer. And instead of calling the constant 1/10 k, I just renamed it capital C. Alrighty, so there you have 3 examples. And here is a copy of your worksheet, because this material is not in Edwards and Penny, so I've taken these problems from Ellis and Gulick, and these will be sent to you by email if you're in my course, and I will also probably post it on Google Docs. And here are the answers to the odd problems, and so I guess you know what I'll be doing with the even problems. Do you? Do you? And so I leave you with a little humor, a little calculus humor. There are only this many kinds of people in the world: those who know calculus and those who don't. See you next time. Bye-bye.